I'd like to basically start the first talk, which will be, so maybe the next slide, I guess, or yes. So before we start the first talk, actually, we need to have a note taker. So that is going to be a 30-minute presentation, during which you don't need to take notes. But during the 30-minute discussion, we need to note-taking volunteer. So if anybody wants to volunteer, what they can do is either chime in now or use there's a feature here, go into the chat window. You can basically, I think, raise your hand. There's a reaction or a method to raise your hand. Does anybody want to volunteer right now? It's okay. We can basically move to the presentation and then I'll ask again at a later. So why don't we start with the first talk. Next slide, I guess. Which is hardware accelerated modular multiplication for ZKProofs. And the talk is going to be given by Erdinc and Justin. And so, and the papers by Erdinc, Justin, Sean, Simon, and Kelly. And let me just give a brief introduction to Erdinc and Justin. So Erdinc is an assistant professor at Sabinci University, or Sabanci University. Erdinc, please correct my pronunciation when you take over in a second. Sabanci. He's currently working on hardware and software acceleration for cryptographic primitives. His main research is lattice-based crypto, fully homomorphic encryption, post-quantum crypto, and with a focus on computer arithmetic and architecture. Justin, he's a research Ethereum Foundation working on M2's L1. He's interested in public good cryptography, such as aggregatable signatures, VDFs, SNARKs, etc., and mostly in helping bringing those to production, the benefit of the wider blockchain ecosystem. So with that, why don't we let Erdinc and Justin talk. So I think Erdinc, you can take screen share.
You're muted, Erdinc.
Erdinc, you're muted.
As many times as we practice this, you know, it can go wrong when it goes live, so.
There you go, I found it, okay. Sorry, is it on full screen?
Yep.
Okay, perfect. Hi, I'm Erdinc. I was introduced. I'd like to introduce the other team members, Simon Peffers, Sean Gully, and Kelly Olson in the project. They constructed the company Supranational, and we've been working on the project for verifiable delay functions for the past year altogether. And we came up with this paper. Okay, so the outline of the talk would be, first I'm going to talk about why we need acceleration, hardware acceleration for anything, basically. And I'm going to give an introduction to RSA and ECC primitives, just to give you an idea about the complexity of the actual implementations for, like say, cryptographic primitives. Then I'm going to talk about some high-level algorithms that are used for acceleration for these things. Then I'm going to talk about the platforms that we targeted for acceleration for speeding up these primitives, CPU, GPU, FPGA, and ASIC. Then I'll give some performance comparisons, and then Justin will take over. So, introduction, why accelerate? Okay, so conventional cryptography is a well-studied field. It's been, there's a lot of material in literature. So what do I mean by conventional cryptography? Right now RSA is being used everywhere. ECC is being used for as public key cryptography, and there are symmetric key cryptography, advanced encryption standard, and there are other algorithms. So they're all well studied. So they're, let's say, tailor-made for different applications. But the applications are, let's say, they have set, let's say, constraints. For example, RSA. We need to speed up RSA on the server side because server will have to work for many clients at the same time. So the throughput for RSA operations is very important for the server side. But on the client side, the latency or throughput is not that important because a general user only connects to a website maybe every depending on the usage, every second, every minute. But when you're talking about the milliseconds range, it's not that important to accelerate these things on the client side. So just an example of the constraints. Of course, there's many more constraints. It's just what I'm trying to say is, conventional cryptography is well studied, but it has its own constraints. So innovation in cryptography is enabling new capabilities. So with the new cryptographic, let's say, primitives, BDFs, SNARKs, accumulators, all the things that we've been talking about, even in this workshop, new capabilities emerged. Okay, new constraints emerged. So these constraints were not addressed for the, let's say, the current literature. So that's why we needed to work on accelerating these things. For example, VDF, verifiable delay function. It's based on exponentiation, just like RSA, but for a verifiable delay function, the most important metric is latency. Just a single, computation for just a single modular exponentiation. It has to be as fast as possible. So that's a new constraint. That was not a constraint that was well studied in literature. So we had to study it. We came up with some good constructions. And right now we're working on an ASIC construction for those VDFs. So just an example. And most of these are computationally intensive, these primitives. And acceleration enables higher security because we can have larger key sizes. Even with RSA, if we have acceleration, instead of using RSA 4K, we can use RSA 2K, we can use RSA 4K without affecting performance that much. So greater scale can so the throughput can increase with even on the servers if we have accelerators for these things, and there are accelerators for some applications. So it will be more scalable, the cost will be lowered, etc. So we had to examine these cryptographic primitives, and for the public key stuff, the same large integer arithmetic is fundamental across most of the operations, let's say, algorithmic families. So for RSA and ECC, the most important algorithm is large integer arithmetic. Okay, so what's our, let's say, recipe for acceleration? What do we do when we decide to design, let's say, an accelerator for any topic? First thing we do is we define the use case. This is what I mentioned. So SNARKs and RSA accumulators, VDF, they don't need use cases. So we define the use case, and the use case will define the constraints for the implementation. Let's say it's not just about mathematical functionality anymore. It's just how you bring it to the reality with good enough, let's say, performance. And then after that, we define the use case. We benchmark and profile to find bottlenecks. We get the state-of-the-art implementation for for any of these algorithms, let's say. And then we benchmark them and we find the bottlenecks, we find the problems. We find the issues with the new constraints, let's say. We have to identify the issues with the new constraints for these problems, the unsolved, let's say, set of constraints. And then we need to identify the underlying key operations. This has many levels. There's, looking from a high-level perspective, for example, I just mentioned the underlying key operation for RSA is modular exponentiation, etc. But for modular exponentiation, the underlying key operation is modular multiplication, and it can just go on. So there are many levels of identifying the underlying key operations to accelerate, and many different, let's say, approaches can be taken here. And they have to go together. That side by side cannot be. You can't just go and optimize for the lowest possible, let's say, level and hope that it works for the higher level. It has to be. These all have to go in sync. And then we select the platforms based on required performance characteristics. This is if we have to build the entire system ourselves. We go select: are we going to use a CPU, FPGA, GPU, or ASIC? Or if somebody has, for example, a system that includes a GPU, how do we go and accelerate that system as much as possible? So the target platform selection happens at this level. And then we carefully map the operations onto the capabilities provided by the target platform. So this is a whole system level approach to doing acceleration. There's no single, let's say, answer to any problem. There's no turnkey solution to any problem. It's most of the time it's custom made for a given set of constraints. Okay, so this is on this screen, on this slide, you just see examples of the stuff that I've been talking about. There are some use cases: time blocks, anti-spam, MPC ceremony, etc. And we have hardware platforms: CPU, GPU, FPGA, and ASIC. They have different, let's say, performance metrics, different functionalities, different levels of resources on them. Even in one family, there are many different, let's say, many different components that have different, let's say, amount of resources. On CPU, there are, there's a 4 gigahertz CPU versus there are 1 gigahertz CPUs. So different metrics. Arithmetic algorithms, for our case, for most of the topics that we studied, it's always about modular squaring and modular multiplication. These are the most, let's say, time-consuming operations for RSA, for ECC, for the stuff that we worked on SNARKs, etc. It's all about modular scaling and modular multiplication. Of course, there's addition, subtraction, etc. But these are the most, let's say, time-consuming primitives. There are cryptographic constructions and assumptions. So these are all just examples of what we've been working on to come up with an accelerator, let's say. So RSA primitives. RSA consists of modular exponentiation. So exponentiation is calculating x to the power of y. So this operation is not, the most optimal method is not just multiplying x by itself y times. Y can be a 10 to the 24 bit value. So multiplying x by itself 2 to the 10 to the 24 times is not possible. So that's the definition of it. But so that's the RSA primitive, and how we implement it. The simplest, one of the simplest methods, let's say, is square and multiply. So what we do is we get y, the exponent. We write the binary form of the y. We scan y from top to bottom, bitwise, and we initialize a variable with 1. So for every bit in the exponent, we square that variable, and then if the current bit position on the scalar is 1, we just multiply it by x. In the end, we get, for example, if y is 10 to 24 bits, if y is a 10 to 24 bit value, after 1024 squares and almost 512 multiplies, we get x to the y operation. Even the most trivial, let's say, square and multiply approach is much faster than multiplying x by itself y times. PDF is a special form of exponentiation. It's just basically calculating x to the 2 to the t, repeated square. So you get x, you square it t times. The property of VDF, verifiable lift function, is that the fastest method of calculating, the fastest way of calculating this x to the 2 to the t is just repeat the squaring t times. There is no faster way. There are many different exponentiation techniques. See, this is the highest level I'm talking about after modular exponentiation. How do we do modular exponentiation? We can use left, right, square, and multiply with windowing, etc. But these all rely on large integer modular arithmetic primitives, square, multiply, add, and subtract in the end. What we're trying to do here with this high-level optimization of modular exponentiation, this square and multiply with windowing, etc., is reduce the number of multiply and square operations that we do in the end, not optimizing multiply and square by themselves. This is just to reduce the number of low-level primitives that we use, the high level. So once we optimize this part, once we reduce the number of primitive operations, we can go and optimize the low-level versions. ECC looks very much like RSA. I mean, it's totally different math. Everything is very different than RSA. But the thing is, the underlying math, the high-level construction is exactly the same with ECC. ECC consists of scalar point multiplication. You just say Q is equal to K times P. And all exponentiation techniques can be used for scalar point multiplication. So, and the only thing is the primitives are replaced. Instead of modular squaring, we do point doubling. Instead of modular multiplication, we do point addition. Other than that, everything is exactly the same. And point addition and point doubling operations rely on, same large integer modular arithmetic operations. But with only one thing difference is the smaller operands. They use smaller operands in the range of 256 to 512 bits. And whereas RSA, currently we're using RSA 2K, and for very, very high security, we use RSA 4K. And one major caveat is point at infinity. I said, ECC looks very much like RSA, but the only thing is ECC does not have a zero element. Let's say there's this point at infinity. That's something that needs to be taken care of during implementation. I just want to put it there. We can discuss later. So latency versus throughput. This is one of the considerations when implementing, let's say, cryptographic primitives. So latency oriented is performing an individual task as quickly as possible. So for one task to be, for this one, single task has to be finished as fast as possible. And I just gave the example, VDF evaluation, the squaring portion has to be completed as fast as possible. So this is a latency oriented problem. So area of the resources that are used can be really high, but the latency has to be very, very low. It doesn't matter if I can do n operations in a second. What matters is how many. So how long does it take for a single operation? Throughput oriented is how many operations can I do in a single, let's say, second. That's the throughput oriented. Single latency is not that important. But the number of operations that I can do in a given time is important in throughput-oriented implementations. I gave the example at the beginning, the RSA on the for example, server CPUs. That's a throughput-oriented problem. So the picture is showing just a very simple example. So we can. Just by pipelining or just improving, let's say, the logic behind the implementations, what we can do is either see the first one is latency oriented, so it's very, very fast, and 4 problems takes some certain amount of time. In the second picture, as you can see, that latency for each operation is increased a little bit. It's like 1.5x, but overall, almost at the same time, we can work on 12 problems instead of just 4. Okay, so performance implementation algorithms can lead to orders of magnitude difference in performance, the high-level algorithms and the low-level algorithms. Here I'm showing some mix of both high-level and low-level algorithms implementations. For example, modular square and multiplication, this is the low-level one. For the basic primitives of all these implementations, we need really, really fast and efficient, not just fast, really efficient, let's say, modular squaring and multiplication operations. And for reduction, we use Montgomery and Barrett. We explore both of them. And for multiplication and squaring, we use different schoolbook, Compaq, Karasuba, Shonaga, stress and algorithms. For exponentiation, again, I already talked about. There's binary square and multiply, Montgomery ladder, sliding window. The difference between these things is that they're just trying to reduce the number of basic, again, operations. There is multi-exponentiation algorithms, and there are variations in multi-exponentiation. Design considerations. So what are those variations in multi-exponentiation? We have many different flavors. So it can be different base, different exponent, same base, different exponent, different base, same exponent. And this is on the top, we're showing it for modular exponentiation, and on the bottom, we're showing it for ECC. They're actually exactly the same thing. As I said, exponentiation G1 to the X1 is similar to doing K1 times P1 in terms of high-level arithmetic. The low-level arithmetic is different, yes, but in terms of high-level arithmetic, they're different. So multi-exponentiation does not have a single answer. As you can see in this picture, there are many different variations. And even within these variations, there are different schemes. It could be addition of these, for example, points on the bottom. It could be just, you would need the entire, let's say, all the results from all the scalar multiplications. So many different flavors, and with different flavors come different answers. Again, there is no single turnkey solution here. This is just an example for multi-exponentiation. We have to do 4 operations, K1, P1, K2, P2, K3, P3, and K4, P4. And here, if you can do, them side by side, just do, let's say independently from each other. If you do that for single exponentiation, in total, you require 4 times 7 doubling operations and 20 addition operations in total. But if you do multi-exponentiation, and this is how you do multi-exponentiation, is that you initialize with one of the points here, and then you add, let's say you initialize with P1, and then you add P2, and then you add P4 on top of it. And then you double the result. On top of the result, you add P2 and P3, double the result. On top of that, you add P1, P3, P4, and double it, etc. And this is a very simple interleave approach. This is Shamir's trick. Very basic implementation, single bit implementation. Even this is giving, say, point doublings went from 4 times 7 to just 7 operations. So this is almost 2x improvement over the basic one. So there are many other methods. See, in single, the windowing methods can be used here with different approaches. So the number of the operations that we are doing also changes the fact how we do the high level let's say multi-scalar multiplications, multi-exponentiation, let's say. The reason we use multi-exponentiation for scalar multiplication is because they look exactly the same from the high level. So this is how large integer arithmetic looks like. So this is the primitive that we actually want to accelerate. So on the left, you see, add and subtract. You're adding or subtracting 2 large numbers, and on the right, you see the multiplication. We have to break down the operands into limbs, because doing an entire, let's say you have to do 1024-bit multiplication. It's really hard for any piece of hardware or software to just open up just a single 1024-bit multiplication. In software, you can't do that because the underlying CPU only has 64-bit multipliers anyway, so you have to do an algorithm. But if you want to do just to build a single hardware that does 124-bit multiplication, it's going to be really, really slow because of the air propagation delays, or it's going to be really high in area. So we break down the algorithm into pieces, as limbs shown on the right. And so we try to optimize all the multiply and add operations as much as possible. The one on the right, we're seeing a CPU implementation. So a forward number is multiplied by another forward number. And so each time, so these are 64-bit limbs, let's say. Each time we multiply, we get 128-bit limbs. And see, we can add the low parts together using ADCX instruction, and high parts together using ADOX instructions. ADCX and ADOX instructions were added to the Intel CPU just to speed up this large integer arithmetic. They have independent carry chains, let's say, and carry chain is a big problem on CPUs. That shows dependency between instructions that are running on the CPUs. So ADCX ADOX is giving you just 2 independent carry chains, which speeds up this addition operation on the bottom almost twice. Sorry. Okay, so see here we talked about multiplication. On the left, you see the multiplication operation. This is full book multiply. This is very regular structure. And on the right, you see the squaring operation. The only difference is the bottom triangle. See here you don't have to do y0 x1 and y1 x0 together. we can do x0 and x1 once and just multiply it by 2 at the end. Multiplying by 2 is just shifting it left by 1. So the light purple partial products here that you see on this picture are doubled after the operation. But see x0 square, x1 square, x2 square, and x3 square, they're not doubled. So there is an optimization for squaring. Sorry, if you're implementing especially for squaring. And if you're doing any of these operations, if you're doing RSA, ECC, even the stuff with anything elliptic curve based with SNARKs, it makes sense to go and optimize for squaring. So this is showing the intensity of the operations for large, let's say, operands. So on the left, schoolbook multiply requires 1024 operations in total. On the right, square requires 528 operations, and this is for 2K-bit, 2K-bit operations on a CPU, multiplying two 2K-bit numbers versus squaring a 2K-bit number. And the larger the numbers get, the higher the gain. The higher we have the gain for specialized, let's say, squaring implementation. So platform comparison, the summary of all, everything I talked about is, it all boils down to modular multiplication and modular squaring, RSA ECC based implementations. There are different variations with high-level optimizations, let's say. In the end, at the high-level optimizations, all we do is try to reduce the number of modular squarings and modular multiplications that we do, and try to parallelize them as much as possible, so that when we send them to platforms that have really high resources, those platforms can run them in parallel very efficiently. This is an example for a 2K-bit multiply on a CPU. In the picture, you see a CPU architecture. This is an Ice Lake microarchitecture from Intel. See, it has a single, every core has a single multiplier, 64-bit multiplier, and with the new AVX512 instructions, there are IFMA instructions. Those IFMA instructions include 8 52-bit multipliers. So there are limited resources on CPU, let's say. I mean, yes, the 64-bit multiplier is powerful. The AVX512 stuff is also getting powerful, but there are limited resources. So with 8 cores, with a multiplier size of 64-bit, and with a frequency of 5 gigahertz after turbo, and our theoretical throughput is 39 megaops per second for 2048-bit multiplication. This is a GPU architecture. So frequency is lower than the CPU, 1.5 gigahertz almost, so 1545 megahertz. And multiplier sizes are small, 32-bit multipliers, but there are many cores, not just 8 cores, there's 4,600 cores here. But in the theoretical throughput that we get is 1738 1.7 gigaops per second. It's much higher than the CPU. See, latency is latency is larger here for this, for GPU implementations, because we have the 32-bit multiplier and we have the lower frequency, but because we have many cores that are running together, and because we can parallelize the problem of large integer multiplication, the throughput is much higher than CPU. And FPGA, these are the basic building blocks, let's say, inside the FPGA. We have DSP blocks. Of course, there are other CLB blocks, but these are for the multiplication and accumulation operations. There is a 27 times 18-bit signed multiplier, and these can be used for 26 by 17 unsigned multiplication. And there is 6 for the platform that we've been using. This has there's 6,840 of these let's say blocks. The frequency is much lower. It's 462 megahertz per block, let's say, but and the throughput is much smaller than the GPU. It's 327 megaops per second, but it is higher than it is higher than the CPU. CPU with 5 gigahertz gives 39 megaops per second, but an FPGA with 462 megahertz gives 327 megaops per second. And this is the study we did. For a basic estimation, if we build a custom circuit for doing this operation, 2k bit multiply, just doing this thing, just doing a 2k bit multiply, and if you build this circuit for if we build the circuit for the, let's say, highest technology with a frequency of 1 gigahertz, we can get 15 gigaops per second, which is 15.6 gigaops per second. And we can have different variations. We can have a low latency design, or we can have a really high throughput design, which is the high throughput design, which will be a smaller version of the the larger one, with which will be reused as the core multiplier, like we do in the CP implementation. So performance impacts. So CP example, on the CP, I gave the example of ATCX and ADOX instructions. With ATCX and ADOX, the performance of large integer arithmetic improved a lot on the CPU. And there are new instructions that I just mentioned, which has 8 lanes of 52 by 52 plus 64 operations. We just started working with these ones. Hopefully we'll get some performance results from these also. So these are, this is just the graphics for the throughput for 2K Montgomery multiplication. As you can see, GPU is dominating for throughput. And this is, see, for this one, GPU is dominating. But if you build an ASIC chip with almost 200 watts power usage, throughput will go to almost 8 gigaops per second. So this is showing the latency. See, GPU has the highest latency, which is the first case for latency, and again, ASIC has the best possible latency, let's say, potential here. So custom-made ASIC has shows the best performance, yes, but it's really expensive to build. So so there are different platforms, and yeah, the summary is different platforms and different design considerations here. For throughput, the answer is for throughput, GPU might be the quickest answer, and for latency, here FPGA might be the quickest answer. Okay, this is the end of my part. I'm gonna hand it over to Justin.
Thank you, Erdinc. So let me share my screen. Okay, so basically a lot of this work that we've been doing to analyze the performance of modular multipliers, it's partly for the VDF project, but also for this Abhi project, which is basically the idea to try and build an ASIC to make SNARKs super fast. And more specifically, what we're suggesting today is like a multi-exponentiation ASIC. So this is kind of the Strawman proposal for discussion of a possible kind of ASIC. And I guess in the context of standardization, ASICs are kind of standardization by brute force, because if we do succeed in building an ASIC, then we'd get huge orders of magnitude gains, like 100 or 1000x speed up, and so there would be a big incentive for people to adopt our technology. So whatever choices we make, might have an impact on what is actually used in practice. So one of the suggestions that we make is that the ASIC focuses only on multi-exponentiations and not on the FFTs and not on the witness generation, which are the two other parts of computationally expensive parts of SNARKs. And I guess the reason we're suggesting that is that, like, I gave a talk recently for the ZK summit on basically taking Planck and removing the need for FFTs. And I think a lot of the techniques that I've shown there are relatively generic. So maybe you can take the Groth 16 scheme and remove FFTs there, and so in the context of hardware acceleration, you get a significant simplification if you focus on one thing and do it super well. Hence why the multi-exponentiations only proposal. the other thing that we're suggesting is that the ASIC is only capable of doing multi-exponentiations for the one curve, BLS12381. So BLS12381 is being standardized by the IETF. It's a blockchain standard, which is adopted by ETH2, by Chia, by Filecoin, Algorand, and others, and Zcash, of course. It's secure, and as we've learned recently, and that's great for hardware, is that it's efficient to do recursion in BLS12381. So for a long time, the thinking was that you need these crazy like cycles of elliptic curves, or you need curves like BLS12377, with special structures. But thanks to the research of Aztec and things like ultraplanck, actually recursion is not that expensive. On the order of 1 million gates. Maybe even less than 1 million gates. And so 1 million gates when you have an ASIC is just absolutely peanuts, because you can do exponentiations on the order of size 1 billion in just 1 second. So 1 million gates is nothing. One of the advantages of the SNARK ASIC is that we don't, relative, for example, to the VDF ASIC where latency is critical for security. Here, there's no performance is merely a good thing to have, to lower cost, to lower latency, to increase the size of your target circuits, but it's not critical that you be the absolute fastest. And so you can afford to use a relatively cheap process technology, for example, 28 nanometer, which doesn't have anything fancy like FinFETs. And what we suggest is basically that we build this PCIe card, which has the ASICs, and you can just plug it in to PCIe slot. And we suggest using PCIe 4 because it's high bandwidth, it's cost efficient, it's convenient. To just plug in an existing setup. And one of the other ideas that is being put forward is, so basically when you want to do an exponentiation, there's two pieces of data that need to be communicated to the ASIC. On the one hand, you have the basis elements. So this could be an SRS, like a powers of tau, or it could be an SRS, which is in the Lagrange basis. So basically these are G1 elements that you need to communicate. And these G1 elements tend to be quite big, maybe 96 bytes per element, if you're working with BLS12381 and the points are uncompressed. And then you also have coefficients, which are 128 bits. And so because the SRS is fixed, you can just write it once in RAM, which is on this PCIe card on board, and that can be read directly by the ASIC without having to basically overload the bandwidth of the PCIe channels, which are limited. And so the diagram here is basically that you have the ASIC in the middle that's fetching. Well, that is given coefficients by the host, connected via PCIe. You max out the bandwidth of PCIe 4, 16 lanes. That's 20 gigabytes per second. That allows you to do roughly a bit less than a multi-exponentiation of size 1 billion in just 1 second. And then you're also reading the SRS from onboard RAM, at a rate of 60 gigabytes per second. So that's kind of the technical stuff, but there's also, I guess, non-technical things that need to happen, for an ASIC product to be successful. One, we kind of need a team that can deliver the ASIC, and I'm not part of Supranational, but I've been working with them for over a year now on the VDF project, and that's worked out very well. I trust them to deliver, to work on the next project. And I think we have the opportunity in the blockchain space to basically make this SNARK ASIC a public good. So, you know, the upfront cost is on the order of $5 million, let's say. And I think that's something that can be subsidized by various blockchain projects, and I'll talk about that. And then I think it makes sense, you know, to just sell these PCI cards at cost. You know, we're not looking to make profit here. We're just, you know, looking to provide a value to the ecosystem. Of course, you know, we want to try and be aligned with the open source culture of the blockchain space. And one of the things that we can do at a minimum is basically open source the RTL, which is basically the source code that specifies the logic of the ASIC. And in terms of timeline, you know, it's good to plan early for these things. So, you know, 2023 is my Strawman proposal here. And basically, it's something that we could do kind of in a sequential fashion. You know, first we get the VDF ASIC done, and then we can focus on the SNARK ASIC. And in terms of funding, you know, there has been like support so far from the different foundation in terms of funding this, you know, with others. And here, you know, I guess we can learn from the VDF project, which is now being funded by 5 different projects. So we have Protocol Labs, the Natural Science Foundation, the Tezos Foundation, and the Interchain Foundation. And I'm hopeful that, you know, $5 million is something that can be funded across the ecosystem. So here are some of the open questions for discussion. Maybe the one question that I'm very curious about to hear feedback, because it's the one I'm most unsure of, is the witness generation. So if we have a SNARK prover where you remove the need for FFTs and you only have 2 things, the exponentiation and the witness generation, and basically you remove the multi-exponentiation because you have, you know, a factor of 1,000 speed up, basically what you're left with is the witness generation. And from what I understand right now, witness generation takes, let's say, 1% or a few percentage of the overall time. But that's not truly satisfactory, because if it takes, let's say, 1% of the total time and you remove all the rest, then, you know, witness generation will be your bottleneck, and the maximum speed up that you can get is a factor of 100 speed up. And then, you know, a factor of 100 speed up is nice, but, you know, basically the question I'm asking is, if we were to focus exclusively on witness generation, how much can we optimize it? And I'll skip some of the other questions because we're out of time. And I guess in terms of non-technical questions, maybe my top question here is, you know, who would be interested in funding this? You know, I imagine that some of these names that I mentioned in the previous slide would be interested in funding, but that's a discussion that needs to be had. Okay, and I think we're ready to take questions.
So thank you, Justin and Erdinc. So there are a few questions in the chat window. Why don't we let the first question, Stephen Holmes had a question about side channel attacks. Do you want to go ahead and discuss it, Stephen?
Sure. It was just a question really, is as you improve the efficiency, the danger is, you know, is it really constant time? And if it's not constant time, what does that mean in terms of a side channel attack?
Yeah. Go ahead, Justin.
No, I was just going to say that specifically for the VDF project, there's no side channel attack here. I guess there's no secret. And for SNARKs, yeah, you might have secrets. Like maybe you have a zero knowledge SNARK and you want to protect the integrity of your circuits, of your secrets there. From what I can tell, like constant timeness is not something that's focused on so much in SNARK proof generation. I mean, one easy, actually no, now that I think about it, other than the witness generation, the rest should be constant time. You should be able to make it constant time because the multi-exponentiations have a fixed size, etc., etc.
I mean, time is not the only side channel.
Sorry, say that again?
Time is not the only side channel. But right. I guess unless an attacker can eavesdrop on the connection to the ASIC, which is you're kind of hosed anyway if that happens.
Just to be clear, the ASIC design is probably going to be side channel free, at least timing side channel free, right?
I don't think, well, maybe. I don't think that's one of the goals, but it might be kind of as a, just because the simplest way to build it is as something that's constant time.
So actually, I've forgotten to mention that we need to have a note taker. So does someone want to volunteer? There is actually a very nice link here. I think Daniel has posted it into the chat for note taking there. Can someone who's interested and a fast typer chime in?
I'll do it.
Oh, thank you. So Dara, you also had a number of questions basically pertaining to...
I'm not sure that there were actually questions, more comments. I know I've got to rearrange my windows if I'm going to do the notes as well.
Well, yeah, I wanted to give you a chance. So if you didn't have a question, that's fine. I guess you're making points about these curves, but...
yeah, so I guess I do have a question. So BLS 12381, yeah, it's a really useful curve. It's commonly used, but is it still going to be commonly used in, say, 2 years?
Well, we don't know, but it looks like it is the default kind of blockchain standard for new projects. So I mentioned Ethereum 2.0, Filecoin, Cardano, Chia, but I believe Cosmos, Dfinity, and again, on the topic of standardization. So there's the IETF. We made a big effort on the IETF standardization project to nail down every single detail, and kind of agree within the blockchain project to use a specific draft. So we're going to be using draft version 7 for the #2 curve and draft version 3 for the BLS signatures. And there's also this idea of standardization by brute force. So Ethereum is kind of this big entity in the blockchain space, and just us doing it is kind of forcing the way forward. But we can emphasize this even more with an ASIC where we can sell to people. If you use BLS 12381, you get a 1000x speed up versus using a CPU. That's a way to make sure that it's actually useful, actually being used in 2 to 3 years.
Nir, you had a question about recursion?
Yes, I was just mentioning that if you want to do recursion, if you want like Coda does, you will have to use at least 2 different curves, and I think BLS cannot be one of them because it has to have some kind of connection between these curves. The question is why? So
that just to this is kind of like a common misconception, which I guess is not your fault because very recent research has changed this fact. So if you look at ultra-Planck, which is kind of a technique to do batch range proofs and things like that, that was introduced very recently, just a few weeks ago by Aztec. They were able to use a single curve, namely the BN254 curve, and express the verifier for Planck in only 200,000 gates. So the mantra before was that if you don't have these cycles of the curves, then it becomes horrendously expensive to represent this verified circuit in the proof system itself. But it turns out that that's no longer true, thanks to basically engineering advances that have improved the state of the art by roughly a factor of 10x.
Okay.
So I guess I have some skin in the game here because as a designer of Halo, but there's still a big advantage to using the cycles of curves because you're still getting, say, probably 10 times improvement in circuit size for the recursion threshold. So you may even end up that unless your ASIC is very efficient, your software or GPU implementation of a system using cycles might be better than Plonk on an ASIC.
I would also like to ask, why do you constrain yourself to this curve? To a single curve, yes, let's say. I mean, you have two parameters that you need to think about. The first one is the size of the curve. I mean, if you want to use the curves that are bigger than others in terms of number of bits per curve, and the second one is per specific size, the specific module. I understand that you might want to stay with a fixed size. I'm not sure about changing the modulo for the given size.
Right. I mean, curves are extremely complex. There's like all sorts of families, and it's not just the bit width, but it's also like fundamentally different types of families, right? The BLS family is different from the BN family and the other families, I guess. And the more choice you have, the more complexity you have in the ASIC, and complexity manifests itself in various ways, like less power efficiency or greater area, but maybe more importantly for us is like more R&D and more kind of risk of failure potentially, and just more time to actually deliver the ASIC because it's more R&D and more costly. A practical way forward is just to look at the set of curves that are used in practice. There's the BN254 curve, the BLS 12381, 12377, and then there's these cycles of curves, and then there's curves that are used in Halo. And what we're seeing is that, for example, Coda, they've just dropped the cycles of the curves idea. They tried it very hard, and then they dropped it. And we're also seeing the ecosystem drop the BN254 curve in favor of the BLS 12381.
Have they actually dropped it? The last time I heard, they were using Pickles, which still uses the half pairing cycle idea.
Right, but the curves that they're using previously, like
they're not using the MNT46 curves.
Exactly, right. So
but it's still a cycle, and it still wouldn't be able to use BLS 12381. You can't use BLS 12 curves for the half pairing cycle. You have to use BN curves.
Well, that's unless you're very, very clever on the circuit representation, right?
So you can use ultra Plonk, but that's different from what Coda are doing, what O1 Labs are doing.
I'm sorry, I've got a question. Why you cannot use any VLS curve with a half pairing friendly cycle? Why only?
It's because it's not prime order. So a BLS 12 curve has a row value. That's the ratio between the field over which the curve is defined and the scalar field. The ratio is 1.5 roughly. So whereas a BN curve is prime order.
Yeah. So the way you define the half pairing cycle is not only you need to have a subgroup order equal to the fit size of the previous one, but the whole order of the curve? So,
the Hass intervals have to fit together, and that's why you need both curves to be prime order.
okay, I see. Thank you.
I mean, maybe one thing worth mentioning is that, we're not trying to design something that will match all use cases, just, as many use cases as possible with the resources that we have. But yeah, it will, if we are targeting, 2023 or 2024, then we'll have time to see what is the real adoption, in the market, and try and align ourselves as much as possible.
So we're basically at the time, I believe, for this this session. Is there one more question that someone wants to ask? I see a few in the chat window, but feel free to chime in.
I think if the conversation is going well, maybe we can give it like five more minutes.
Sure.
Cool. Thanks.
So I want to push, if nobody is going to ask a question, but please, if you do have one.
I do want to ask something.
Okay, please.
So you actually started designing this chip, and you have some kind of numbers about other resource needed, let's say internal memories aside from the multipliers.
Yeah, so that's a question for Erdinc.
Understand the.
So he's asking, what are the resources required? Presumably, power, area.
So if you ever design a chip like this, it's gonna be throughput oriented. So it's gonna be operation per watt basically in the end. So that's one of the considerations. So how many operations can we get per watt from this chip? That's one. Yeah, another thing is the memory. How much memory we need is going to depend on the schemes that we want to support. Are we going to put 1 terabyte of memory next to it, which is really not practical, or are we going to put maybe a few gigabytes of memory next to it? But again, that's why, as Justin said, we need to first narrow down the most common things we want to support, identify the requirements for this thing, and then go build necessary, let's say, peripherals that's coming next to it. Even and for the 381, so even for the BLS curve, the multiplier that we put for the BLS curve, with little modifications, it will be able to support many other ECC curves, many other sizes. So we're talking about flexibility here, as much as possible. So if you put like 384-bit multiplier, that can be used for 521, NIST curve with some, loss in performance, fine, but it will be able to implement that also. That's the comment. Yeah, I wanted to. Yeah.
So, to what extent, how flexible are these ASICs in terms of changing what they do using firmware?
See, that's the thing. We need to define. So it has to look like a CPU. So we need to define instructions for these things. It's not like the Intel set of instructions. It's going to be instructions that are specifically tailor-made for this. For example, we can define a 384-bit multiplier instruction, and 384-bit multiply and accumulate instruction, and use that for everything else. It's not going to be in the very coarse level of doing 64-bit all of the 64-bit operations. It's going to be at the high level.
Okay.
Actually,
you're still basically programming.
Yeah, go ahead. Sorry. I'm sorry.
You're still basically programming it. It's not just a fixed slab of hardware.
Somehow, yes. Some firmware programming, yes.
Okay.
You didn't mention modular arithmetic. What kind of how you are planning to do the modular reduction?
We're exploring 3 different techniques: Montgomery reduction, Baird reduction, and lookup table based reduction. The lookup table based we used for the VDF implementation, FPGA implementation. We're exploring all of them at the moment. So again, this all depends on the main operation. So if let's say that we end up with using this thing for all repeated multiply and squaring implementations, then the optimal choice would be doing Montgomery. It's a little simpler than Barrett in terms of complexity. But if you're going to care about, let's say, single multiplication, single operations, single modular squaring, or single modular multiplication operations, if there's any scheme that we want to support for that, then we might have to go and use Barrett. But again, that's a firmware support. That's not a hardware support.
All right. I want to thank both the speakers as well as Dara for taking the notes. So this is the conclusion of this session. Sort of thank you.
Thank you, Abhi, for moderating.
Yeah.
Thank you.
Yao, you want to take?
Yes. Thank you very much, Abhi, for